A once-in-a-lifetime opportunity. Jim Kreuzer, he has the new wireless Pioneer. He's got a large private wireless museum in Elma, New York, near Buffalo. He's been doing this for about 14 years. This is one of those classic cases of a hobby becoming a life's work. He's a rare book dealer by trade. He specializes in antique science and technology books. As a matter of fact, he does have a booth here. It's a wonderful place to go and browse. And he's got all kinds of esoteric books that are in great condition, although he says he keeps the best for himself. He goes to England twice a year to look for other things to buy, and in the process he has some of the little pieces of equipment that you see on the tables here. He writes for several association newsletters. His collection is the largest private pre-1920 wireless apparatus collection in the country. Assisting Jim in this talk will be Jim Hardesty, a friend of his from Ithaca, New York. And Jim will be doing some of the commentary during this talk. So please welcome Jim Kreuzer and Jim Hardesty.
Thank you very much, Michael. I appreciate that. Can you hear us? I guess you can. Happy to be back again with the microphone. I hope we have, I know we have, a great presentation here today. Before we start, one of the things I want to mention is everything here obviously is extremely fragile. So of course we'll hope that we want everybody to stay back, and even when we're finished, we ask you to keep some distance from the table and the things. We'll try to show tubes again and do everything we can to make it a, answer your questions and show you things. But it's very, very important that we observe at least a modicum of distance and respect for the tubes. They've made it over 100 years. They still have their vacuum. They work extremely well. Okay, I think that's easy to understand. Now let me make a statement almost exactly opposite from that and say that those of you in the peanut gallery back there, or wherever that is, will not really be able to appreciate what we have here. And even those of you that are up in here really are not going to get the full value of this. So I would break a precedent, or make a precedent here we've never done before. I would ask you to come in, move your chairs, and come in and be right up with us. Yeah, come in. I think we have to leave a fire lane, but come in and just sort of keep your chairs in the same way. So yeah, Bill and Jim and Mark, come on up here. I want to make sure that everybody gets an opportunity to see this. Those of you in the back, even if you have to stand or sit on top of your chairs, I would like to really give you the opportunity to see all these things. Make sure that the effect is good. For photographs, I have to turn to my friend in science and so on and ask about, if you're going to take the best picture with your camera of these, what would you do? What's the best way to go about it?
Well, for those of you who have a camera that uses a shutter that you can adjust for a bulb setting, that's the B on your shutter adjustment, you need a time exposure. So if you can hold your breath and hold the camera very still, convert your f-stop so that it's wide open. If it's f2.4 or f1.8, whatever is the widest iris or aperture that you can set your lens to, and do a bulb exposure. If you can't do a bulb exposure, if you can do a 1-second exposure, that's also good. But in a setting like this, if you have a high-speed film, or even if you have a low-speed film, the object is to get the longest time exposure you possibly can. If you only have a camera that only shoots a 60th of a second, which is pretty much standard for strobe flash-type pictures, you probably won't get very much as far as the effects of the discharge.
Thank you very much, Bill. Right, okay. Now, what we're going to do, we're going to display the tubes and talk about them, give a historical perspective, and try to answer questions as we go along. I would ask you not to feel shy or held back from asking questions as we go along. Stop us if you haven't seen enough. If you want to get another shot, we're really bringing these tubes out here and getting this marvelous friend here on the airplane and all that was a challenge that I really have to turn to my friend here who got all that together and even encouraged me to do that. What you see here today is, and I really want to say this right from the beginning, is a very special contribution by a friend of mine. Jim Kreuzer and I have been friends for a number of years. Our friendship actually really got started over a rather curious and bizarre situation with an antique radio. Someone down at Cornell was throwing out an early Mignon radio, which actually was manufactured in Elmira, New York, not very far from where I live, and so somebody gave it to me with a bunch of other things and said, here, see if you can take this up to the Antique Wireless Association swap meet, symposium and so on, and get rid of it. So I had a presentation to give, and I took it up, and I was running around, and Jim was running around, and another collector, Lauren Peckham, who would sell his house to get that rig and all this, he was running around, and it turned out that the thing slipped away to somebody else, and everybody flipped out, and so that's where we really began ribbing each other about every time we used to see each other, he'd say, you don't have any more of those Mignons, do you? Anyway, we've gotten beyond that. I think we have anyway. Jim is a marvelous collector. It isn't curiosity that makes a good collector. Sometimes I say it's greed. You really have to get out there and you have to dig and look and look and look and take the time and read and understand where things are and know where stuff should be and where they scrapped the ships and took the old radios off and where this and that happened. This is a gentleman here who has that ability beyond anyone else I know, and his collections are excellent. That's not even a good word for it. It has been my pleasure, and I mean, it's also caused me nausea a lot of times just to see the incredible things that he has and sort of deal with that, I think they call it gut feelings, or I wish I had maybe just a few of them. You know what I mean, Dave, and some of the others you probably do too. To begin. Well, this morning I was talking about the beginnings of this particular kind of glassware, and I said that in about 1674, a gentleman by the name of Picard, working at the Paris Observatory, was carrying a barometer and sloshed around some mercury inside of a tube that was evacuated by virtue of the fact that the mercury pulling down on the barometer created a vacuum in the upper part of the capillary tube. And he saw blue flashes of light as a result of something called triboluminescence, which is the friction of the mercury against the glass, actually liberating some electrons that excited the gas in the tube and produced, when they relaxed, produced a light that was there. And for many years after that, experimenters did all kinds of things with mercury. Francis Hauksbee, for instance, was not only famous for static machines, but he also was famous for his experiments with vacuum tubes with mercury in them, making his own kind of vacuums. That's a good idea, because this really gave me a problem. Vacuum pumps in the early days were, well, the inventor of the vacuum pump, I guess, is Otto van Guericke, who used an early, what would you call it, a fire department syringe type thing. They used to fill it up with water, squirt fires out with it, but he turned the foot valve around and hooked up the end to glass tubes and then began to work it the other way, and he could pump the vacuum in tubes, and thus began experiments with vacuum. But vacuum pumps did not really take on what can I say, didn't become good enough until, I suppose, well into the 18th century and into the early part of the 19th century, where they really got pretty good, running up to the time of a gentleman by the name of Heinrich Geissler. And Geissler, as a matter of fact, this type of tube that you see here, maybe you could hold up a Geissler tube, just named after this gentleman. This type of tube, a glass blower with the abilities to make all these curlicues and twists and bends and take different types of uranium glass and lead glass and German glass and all this and put these in here and then fill them up, pump the air out, have gases such as hydrogen, obviously nitrogen and oxygen present by virtue of the atmosphere, and then be able to pass electrical charges through them and create some lighting effects as a result of the excitation and relaxation of the gas that's within the tube. Geissler had also a tool at his disposal that was not available before Faraday and Henry's time, and it's a tool that we see right here, and this is in the earliest times this was known as the inductorium or induction coil. This kind here, this is another smaller version of it, This particular coil here is it's made by Newton and Company. Actually, Newton and Apps were merged in the 1890s. Previous to that time, coils were manufactured. The famous coil maker Apps in England made some of the greatest coils of all time. Actually, the Spotswood induction coil, if any of you have ever read any blurbs about that huge, if you've been to the Science Museum in London, you see the Spotswood coil, this huge, amazing coil with just infinite amount of wire, produced a 48-inch spark or something. It was quite incredible. This is a little smaller version. This is the 6-inch model, right? The 6-inch Newton. This is very interesting because this particular coil here is brand new. In fact, it came in the box. We had the box upstairs, and so this coil, Jim got it, took it out of the box, and here it is. We figured that if we were going to bring these wonderful tubes up here, that it certainly would, we should try to have it be a class act all the way down the line. So we have a brand new Newton induction coil dating to about 1899, 1895. So this certainly would have been present at the time of the discovery of X-rays and so on. And it would be used, although Röntgen's coil was different than this. This is a 6-inch coil. This is a 1-inch coil here, and we have the smaller coil because we don't need this kind of high pressure to run some of the tubes and heat up too much. One of the things that you'll notice as we go on with this is that I was really enjoying Jim Corum talking this morning just about kind of waxing toward the philosophical about dealing with some of these things and appreciating some of the beauty of them. Every one of these tubes here represents that idea, and as you can see, and if you look at the work of the glass blowers that put these together, goes far beyond just the curlicues and the twists and bends that are available in these things, that go into the minute workmanship in some of the paddle wheel tubes and different things like that, and it is I can't think of a word to describe it. It's really beyond anything that it seems we know about in the latter part of the 20th century. And we would do well, perhaps, to take a look back at some of these things and appreciate it. Heinrich Geissler in the 1850s was an excellent glassblower. Actually, he worked for another gentleman by the name of Plücker, and Plücker was one of the first people to observe the electron. He didn't know that's what it was, but to observe the cathode rays inside of evacuated tubes in which electricity was being passed. Geissler built many things and did a lot of experiments for Plücker, and during his tenure doing that, he also got quite involved, manufactured a really amazing vacuum pump system, the early Mercury type of vacuum pump, which simply is this, that I talked about Picard and the early vacuum pump, that not a vacuum pump, this discharge tube that he had, in which Mercury was pulling down on a capillary tube and leaving a space up at the top of the considerable evacuation of the air by virtue of the Mercury just pulling down on it. Well, Geissler, in his experiments and being a good glassblower, was able to construct this Mercury fall tube, as it's called, this type of Mercury lift or Mercury fall pump, in which you literally pour mercury into a funnel and the mercury falls down a tube, and you have some stopcocks. Essentially what it does is you allow the mercury to flow down until it's running out, and then you close the stopcock that goes to the vacuum tube and open up another one, refill the mercury, then get the air back up and then start again. So the mercury continues to pull down and literally pump a vacuum out of the tube. This, of course, is an extremely laborious process, but it works very well, and vacuums below 10 to the minus third microns could be reached with that. God knows how long you'd have to pump to do it, but I mean, that's how all the early tubes were pumped out. So Geissler, of course, didn't pump all these tubes up to these tremendously low vacuums. A Geissler tube will be working somewhere in the neighborhood of about 1 torr, 1 millimeter of mercury in that particular vicinity, and that's all that's needed to get the effects that are available. At any rate, go on with the history as we will go. Let's show the first tube. I think that, I hope you can see this. I think maybe we want to tilt this a little bit. Maybe we don't. Okay. Actually, I should have, but well, we can do that. Let's let's run this a minute without the tube on it. Well, here's the first tube anyway. I'll cover that in just a second. Maybe we can have the lights down. That's pretty good there. You can see the colors in here. They're not only from just the gas, but they're also because the polarity, rather the gases in the tube, but there are different glasses available so that the electron impact also fluoresces those the different glasses. Reverse the polarity. If you notice when you reverse the polarity, you see what I describe as the positive column all up and through here, and the negative area down here, which is really the engine of the glow discharge, is present down at the bottom there. Okay. Let's unhook that tube, and then I'll just hook the induction coil back up in here, and I'll run it a little bit to show you. These type of tubes, there were incredible numbers of these that were made. I mean, it literally, of course, the problem with these is, maybe you can hold that up so people can see exactly what they were looking. The problem with these is they're made out of glass, so they don't bounce. So most of them are gone, and that's one of the reasons why they're not so available. But you can see the workmanship in that. The question you were asking here is that what are the voltages involved? Well, this is a 6-inch coil. We're only running this on 12 volts. It likes to be run on 18 volts as its maximum amount of voltage. But if you adjust the brake over here, and this depending on how you adjust the brake, you get all sorts of different spark out of it, and we really want to leave the brake, they don't need a lot of spark in there, but let's say that's about a 3-inch spark operating there. Go ahead, you can put that tube in. If that's a 3-inch spark point to point, I guess 20,000 volts per inch point to point is approximately acceptable. So we might be looking at a 60,000 volt discharge across the points of the coil, and that is, we don't need that kind of voltage. We could work on 3,000 or 4,000 volts with those Geissler tubes, but we're working with this. While we're setting that up, I wanted to start with this tube, which I failed to do, although I did show it to a couple people. This is called a scintillation tube, and we figure this dates to the 1820s, 1830s. And I'll try to show this to you clearly. What there is in here is there are a large quantity of lead foil dots that are glued in a circular pattern, so that we're not going to hook this up because this tube is quite old and really not to be worked now. But the discharge that you would get jumping between those little lead foil pieces will travel all the way across the tube. So the size of the tube, you could have a tube of considerable length, and it scintillates. It just gets excited, and it was the first kind of do I dare say directed discharge in the 1830s to make something that looks impressive and that people can enjoy. And yeah, okay, this was only fired by a static machine. That is a machine that induction. Well, in that time, let's see. Well, yeah, you could have had some. Both frictional and induction type static machines were used to fire that. Well, not at that time, but like that was the Toepler, Holtz, and Gray machines. Well, the Wimshurst wasn't until the 1870s, and that kind of machine was used to excite that tube, and it would light up because you would get conduction between the little spaces between the lead foil in there, and that would light up, and that gave you something to at least study about the nature of sparks and discharges. Okay. No, that tube is not evacuated. That is, the ends actually come off that tube. Yeah, that's. Can you all hear me? Do I need to talk into the mic too? Maybe, yeah. Okay, yeah. That's right, yeah, okay. Feels like I have a cigar in my mouth here or something like this. Okay, let's do some more of the Geissler tubes. We'll show you just a few of these Geissler tubes here, and yeah, go ahead, bring the lights down, and we'll again run this. This is just another type. Again, the same kind of glass, German, not just German glass, but there is some uranium glass, German glass, and I guess some combinations of soda glass that are used in here. Maybe I'm wrong about that, but you can see the various types of fluorescence around the edge and the seals and so on. But impressive, and you know, begins to show this area of, at that time, natural philosophy, but develops into the origins and basis of modern physics that we're looking at here. This is sort of the, you know, the beginning things of that. Go ahead, we'll take the next tube. Okay, where do you want to? Okay, now here's a. You just probably pick that up, maybe not. Again, another of that basic type of tube. We can see that a little bit better if we. Whoops.
Thank you. I needed that.
That didn't work out. I forgot the end. Well, there's always that side of it. I was going to pick that up, but okay, all right. Yeah, I'll leave that to you. Well, a little shock is always good. It wakes one up and helps, you know. Okay, go ahead. Okay, let's have the creativity with the manufacturing of Geissler tubes continued, and you see here the next version of a tube. And what was done with this, in fact, let me make it hold that up and make an example of this here. In the continuing process of, there's liquid in this tube, an oily liquid with some kind of dye and coloring in the tube. The idea, of course, was that by doing this, you would be able to change the, you know, I guess the light would refract through there in some curious fashion, and you would get a better effect. And so they had to do some very curious kind of glass blowing to pull that together. And I think the marvelous part of a lot of these is the fact that you know, these things are from the 1880s, I guess, of this thing, that after over 100 years, they still work, they still are in excellent shape. Yes? Well, yeah, this is a, okay, this is a question that I field a lot of times, because people look at a machine like this here, which is effectively an alternating current generating machine. However, the amount of energy it takes at the place where the points make and energizes the primary coil and develops the lines of force that cut across the secondary windings is very weak compared to what happens at break, when those field lines collapse around the secondary and you get a considerably larger pulse. So you do have a basically this produces alternating current, but believe it or not, it really does the one direction, the direction that it flows in as the lines collapse over the secondary windings, is much stronger. So the effects show a DC effect, although it really isn't pure DC. Although sometimes some of these, it is pulsating DC. Yeah, let's see what's the best way to. Well, it's not rectified. It's just that the okay, next tube. This is not the water-filled tube. We'll do that in a minute. Now we see here a tube in which we have internal construction here, and we have a lot of different objects inside, curlicues and twists, and the kinds of glass present in there. There's uranium glass there. There's lead glass here, and they are actually flower vases that are in here. And so the discharge that's at the top, go ahead, the top of the vase kind of looks like a flower. The actual positive column effect that's in there gives you that kind of effect. Both. The fluorescence, when uranium glass in its composition is bombarded by electrons, it relaxes and gives off energy at that particular frequency of light, which is green. If you use Pyrex glass, you get a kind of a blue effect. If you use, as you'll see as we go on here, if you use German glass, you'll get a green effect. In those days, to actually fill a tube with gas was a more difficult thing to do, and they didn't have a lot of the gases readily available. So nitrogen, oxygen, hydrogen, carbon dioxide, so were common gases to fill them with. Okay, I'm going to have the lights back up. Why don't you put this one across the small coil, and I'll show this. This is a you can see the construction of the tube. Let me see here. I can tell by the, I would say this is 1890s or so. You can tell by the way the electrodes are constructed. Notice the intricate, look at the workmanship in the glass. We'll talk about that at the end of the show. The answer is yes. Very limited, but the answer is, you can see the intricate workmanship that is involved in these, the twisting and so on, that are beautiful. I can't answer that question. Well, the oldest tube is the scintillation tube, dating some of the 1820s, 1830s. We have a Delarive tube, but it's not here because the vacuum is gone. What did you say, Jim? That was 1870s? 1870s? Such thin glass, soft glass. It's difficult once, you know. The Christie's tag, yeah. Maybe just stick it out on the wire. That sort of that adds class. The Christie's tag, you know, it gives it that sort of, you know that it's pedigree. No, it's got to be good, you know. Yeah. Now the next thing we'll do is lights again, Darryl, if you will. We're the tube here. Yeah. We're going to fire the... You see the effect now? We get a very curious effect here as the liquid allows the light to be refracted through it. And we have the either polarity. Again, you can always tell the polarity by the blue area back in there, because that's where the negative action is taking place on it. You can leave the lights down. I think we're ready for the... Leave the lights down. This is a vase with a small pineapple above it, as you can see when we crank this on. And you see the way that these were designed was so that the effect of the discharge adds... It's like flowers or different things that are going to occur in here to allow you to experience the... they all work together in the tube. And you notice the little, actually it looks like it's a pineapple or a bunch of grapes, one or the other, something. It sort of fits in above there and all. I should put my glasses on, I can see better. I'm sorry. This coil? Oh, yes, definitely. Yeah, they are. That's one of the reasons why the question was, are these contemporary? Yes, they are. In fact, all of the pieces that are up here with the exception of the battery box, which I adapted from some other wooden things and put together. These are all fairly contemporary. I would say we're talking about somewhere from about roughly the 1880s through about 1910. Oh, a bunch of Crowfoot batteries put together, 2-volt cells, 1-foot cells, Grove cells. There were, good heavens, you know, if you visit any of these old, you know, telegraph museums or out west or anything, they just have these porcelain jars they used to get down. The old, you know, you know, working in the battery room is a very special duty, you know, and you know, to keep them going. So you would have banks of cells, and you would just keep adding cells for whatever you needed, probably somewhere in the neighborhood of, you know, 1 to 2 volts per cell, depending. And then there was a whole chemistry to that, and that was the story. Yes, they are contemporary. As after I guess you know, the turn of the century anyway, there was a change in the construction of these coils because of the nature of wireless work. That in fact you see in a number of the books, they talk about if you want to build an X-ray coil or a wireless coil, and the wireless coil requires much larger wire because they were looking for larger currents. Where the X-ray coils, which this is, did not require large currents. We're looking for large voltages. So the actual, oh boy, that's now we're getting into the real beautiful stuff. I think that's a, yeah. Let him put his finger. That's what we need to do. Yeah, and you can just maybe turn that a little bit so people can. We'll revolve it a little bit so that you can see it. This, I don't think this is so necessary, but yeah, we. Oh, okay. We're gonna do that one too then. Hello? Okay, there we are. Let's see. Oh, yes, that is a lot better. You can keep it up. Yes, right, exactly. Battery plus. Yes, there was, it was sort of, you know, add your own juice to your battery cells in those days and just keep, you know, just add as many as you wanted and add the necessary electrolytes and so on to go. Let's fire this one here so those of us in the back fraternity don't have to, you know, be too stretched out. This is exceptional. Maybe you can give that a little turn. You know, you can see the double lid. This liquid filled, and you can see what's called the positive column streaming through the bottom, and then the various colors. You switch the polarity, see, and then you get the same color, but yet we have the bluer section on the other side. The break on this induction coil is a little noisier than usual, but that's one thing you kind of, okay. What did we do here? Oh, no, don't do that. Let's just give it one of those. Oops. There. Up, just keep, you just have to push it. Fused points, that sort of happens as I use these a lot. Okay, you should actually take that down while because that's really. Well, let me. Okay. I'm sorry, yeah. Oh, here we go. It's hard for me. Well, maybe we'll have... how far I can go here. Oh, okay. Oh, yeah, right, I have the mic, yeah. Well, like I say, there was water with various colorings, mineral oil, and perhaps some 4X special, too, you never know. Alcohol, that would be, but it's This is the granddaddy of them all. This is a Christie's catalog that shows a lot of these. The answer, the question was, do these, I'm sorry, predate, contemporary with, let's see, the Edison light bulb is 1879, right, roughly. These were in existence from the 1850s. Geissler's first, really production of the Geissler tube and so on was worked that way. He made, yes, we'll get to that one in a minute. That's beautiful. Edison, I don't know that. I don't know that. Or maybe you do know that. These were all around at that time. Okay, let's have the lights and we'll display another tube here. This is just yet another level of vacuum tube, Geissler type tube. And this, maybe we can, let me rotate this a little bit. You can see, oh, it doesn't want to rotate. You can see the positive column goes through most of that. I'll turn it around this way. You see it's quite a handsome level of glass blowing. If you notice, the symmetry in this tube, this is not just sort of thrown together. It's exactly in the center. Everything is evenly done. This really is an example of true love of work and enjoyment of some of the wonders of nature here in the area with a vacuum discharge. Truly a fine piece. The flash won't work, yeah. Okay, that's good. Did everyone get their pictures there with that? Okay. It's very hard to get a real good video. Thank you. Yes, thank you. The cameras are not as good as your eyes. That's exactly the answer to that. That's a perfect explanation. Barring going through yes, it's really true. We're in the process now of making a major video production with a much larger collection, doing all this kind of thing, and we've actually had to resort to the friend of mine who's doing the video work is using a great deal of digital enhancement in doing these tubes. And when the video is available, you will, if those of you that get it, will notice that the digital enhancement effects actually get right down into the, well, I'll just say this, it kind of really gets down to the molecular level of what's going on, because you see all these different pulsing and so on happening with the colors. A very curious effect, Now we're moving into, let me just make a couple of explanations here. There was an experiment done in 1803 by a gentleman named Thomas Young. And that experiment was called the double slit experiment, I think that's what they called it. Essentially what Thomas Young did was he cut a slit in a piece of cardboard and shined light through it, and the light came out the other side and shone as a light pattern, just light on the wall beyond. But he cut a second hole in there, and then when the light shone through both holes, instead of just being light on the wall, there was an interference pattern, as we call it, which is a very, very curious experience. I won't burn up a lot of time trying to talk about that, but that, at the time, sort of allowed a lot of the natural philosophers, the scientists of the day, to assume that light definitely had to be, as rather obvious, was a wave phenomenon. And that was okay, and people said, well, that's obvious, and there it is, and so on. Well, as time went on, in this particular studies of vacuum discharge work, and when vacuums that could be achieved became higher, the vacuum inside this tube is somewhere near 1/1,000,000th of an atmosphere, new effects took place. As I said, Plücker, who was the professor for whom Heinrich Geissler worked, had made some curious discoveries about what he called cathodic light, or an emanation of a light beam that left the cathode, the negative element down here, and proceeded forward through the tube. He could see something, and there was, to make this a complicated story short and simple. There was a well, as there was a war of the currents in the 1890s, there was a war of the German school and the English school, whether light was an actual particular phenomenon, whether it was actually made up of some kind of particles in the discharge tubes, or whether it was this was just purely a phenomenon of light waves and so on. And Crooks, the British physicist in the 1870s, developed a series of experiments to try to make the go-ahead touchdown for the English school and show that there was definitely some kind of more than just light waves emanating from this cathode, that there were actual physical particles that were actually emanating from this, and that they had, well, in this case, they could be stopped. And they also, when they impacted on the glass in front of the tube, there was actual heat produced. And this was one of the early experiments that he did, noticing that Crooks, who had created a certain evolution with the Mercury vacuum pump, achieving to a millionth of an atmosphere, was able to get much more astonishing effects. And with those higher vacuums, he was able to study these corpuscles. Later in 1897, J.J. Thomson's famous experiment actually made the discovery of electrons, where you could actually get the E over m relay charge to mass relationship of an electron, really proved by using magnetic force lines and electric force lines to balance out the beam. At any rate, the discovery of the electron. Crooks was aware of this and tried to do a number of experiments to show it. This is called the Crooks Maltese cross tube, and it is probably the most famous of the 19th century vacuum tubes. And what we have here is a Maltese cross in the front of the tube. And you know, Jim, what we might want to do is do it the first time with the cross down. And so this tube is made of something called German glass. Now, German glass is a common soft glass in the 19th and the early 20th century. And we talked earlier about why the colors. And I talked this morning about why Birkeland and other people were just so fascinated with looking at these colors, and then sort of wondering if the aurora and other things weren't the same kind of thing. The Crooks tube, the Crooks Maltese cross tube, we'll demonstrate here, is the first of Crooks's series of experiments to try to show that there was more than just a wave nature to what was emanating from the cathode or negative electrode. We have the lights down. This is a beautiful tube, and we're proud to show this. Go ahead and throw the switch. Now, this, yeah, it really, now that's running the opposite direction, so that it changes. The electron, or the corpuscles are coming from the bottom, hitting the top. Go back to the other way again. You see that? So we have, and look at the beautiful color. The electrons streaming down across here, causing this tube to fluoresce this particular color. And I think you should stop there, actually, because, let me see. We're getting to that. Give us a moment. You would get both effects going on at the same time, and you could still see it, but I've never done it. The thing we got to be careful of here is our old friend called you know what, and I knew we were going to get to this topic at a certain point. I have to say this at this point here. And I didn't do this earlier. I'll take just a second here. We are dealing with tubes that produce, in this particular case, a small amount of X-ray. If for any of you here that are, I'm not gravely concerned about this, but I want you to know that if you sit in front of computer screens, if you go outside with the present state of affairs in the sky, you can get a pretty good blast of things. But right here, there definitely is, with the Crooks tube, there are some small amount of ionizing radiation being produced, and there are some of us here who have had great evenings of regaling all these tubes and such, but not all of you may share that feeling. And if you feel, and I do want to make this obvious to you, I would say that considering the distance, that we're not really talking about any great danger here. But any of you who feel that you don't really want to have any kind of radiation exposure, I guess I have to present this to you at this point, because we're moving into some of these discharge tubes, and perhaps now is the time to move back or whatever. And I'm happy to see that no one is... Okay, great. Where is the screen? If you don't believe me, Ken, this is just an experiment that we'll see. You know, it just maybe. Let's turn the tube this way. I don't get too close to it because the field's pretty high, but maybe we can see. Can we have the lights? Yeah. You getting anything? Well, no, I don't think we want to go that far. I'm just showing, actually, I think there's more of the, put this here to block off light that comes through and see if you see anything. No, what I mean is in front of it so that the light from the tube can't shine through, because there may be a difference. You see, do you still get something? Barely. So it's not really. Okay, let's now move on to the, what happens when you, okay, lights back out. We're going to the, someone, now, so Crooks said, if we have a stream of particles emanating from the cathode, they're moving down the tube and striking the glass and causing fluorescence to occur, then if we stop those particles from doing what they're doing, then we should, in fact, see some kind of a result of a shadow on the front of the tube because these particles are being stopped. So he constructed this tube. How are we doing? Go ahead. And the effect is this. And there it is. There's the shadow created by the... run the voltage down a little bit on that. Let's run this one. Aluminum, I believe, or tin or something. Go ahead, hit it. I want to bring that down. The other way. Polarity. There we go. I want to turn the voltage down a little bit. You see, there's the shadow on there of the... so the electrons are being stopped. This was a really... of course, the Germans said, well, now wait a minute, you know, maybe this is just blocking the light and then casting a shadow on the glass, therefore it doesn't prove anything. So that didn't, so at any rate, Crooks said, well, okay, we'll have to try something else. And so we'll look at that with the next tube here. Down the ways a bit, go ahead, okay. Okay, we can have the lights up again. This is just evacuated to about 1/1,000,000th of an atmosphere. That's called Crooks Vacuum. The fluorescence in that particular case is due to the electron impact on the glass. You can actually feel on that glass wall of that tube that becomes warm. And if you keep firing it with enough voltage, you can actually burn a hole in the thing and break it, so you have to be careful. But yes, that's exactly the case. I would say that tube there is, it's later, it's 1910. Yeah, 1/1,000,000th of an atmosphere, yeah. No, they were still pumping with, you know, 4 pumps. At the 1910, they had 4 pumps, mechanical pumps, and then they were, let's see, 1910. Oh, boy, that's a good question. Let's see, no, they did not until the, let's see, Mercury diffusion pumps, 1920, 25, I don't know, I think, what did they... It was earlier than that. I don't remember exactly. I would imagine this was... They had some very curious circular pumps that they actually got the mercury to circle around. They had a motor on this pump. They could just keep spinning it, and it stepped up the effect that was needed for a mercury capillary pump to take stuff out. Now we have 2 tubes here that are of the bombardment type, talking about some kind of... These are Crooks types, some kind of bombardment where we can again get an effect to take place where... I'm going to move that out just a little bit so that it doesn't excite get the glass. Oh, that's probably all right. We'll run that one first. This is a conch shell. Is that what's in there? This is a piece of conch shell brought in and put into a bezel of some sort inside the tube. Again, the vacuum, and then somewhere near about 1/1,000,000th of an atmosphere. And we get electron emission from the cathode of the tube, running down and striking the shell, causing some level of fluorescence within the atomic structure of the shell itself. We're going to excite the atoms of some of the parts of this shell. Could have the lights come down now? I think a picture's worth 1,000 words here. 10,000 words, whatever. Go ahead. And this you can see the level here of, it's very curious. Now if we reverse that, we can still get the thing to fluoresce. The electrons are coming from the top. Actually, this is the proper polarity of the tube, and you can see, perhaps if you look, that in the bottom of this tube here, there is a shadow being cast on the walls of the tube from the green, in green, the shadow of this conch shell in there, because again it is stopping the flow of electrons from hitting the German glass in the tube and giving that effect. Now, okay, that's good. This tube over here, this is another step in the Crooks style. I mean, Crooks, I can imagine for about, I don't know, 15 or 20 years in there, they spent a tremendous amount of time trying to find one thing after another to really keep showing this different effects that were happening as a result of the bombardment by, they weren't called electrons then, but this mystery thing that was going on. This, we can have the lights down again on this. This is really acceptable. Let's put the actually, oh, that's probably all right. I was going to say that the rocks are up. This is a bunch of fluorescent, see here? See that? And some of the actual powder from these phosphorescent materials in here are on the side of the tube, and you can see it. And the thing, and actually, yeah, turn it out. Watch when you turn it off. They'll take a second for them to relax. Now, talking about the coloration of the glass under the bombardment, if you look at it, see, it's still glowing. See this? It's still glowing. So we're taking this. It takes time to relax here a little bit. Go ahead. Yeah, you can. You're going to need to crank that. I don't know what they are right offhand, but what they put in there. That tube was made at the turn of the century. But you notice we've got all sorts of different colors. And like I say, the tube, this tube is later, it's not made of German glass. It's probably made of lead glass or something. And so it isn't fluorescing that green, which is actually good because we don't want to have too much of an effect to shadow the effect of the actual rocks in the tube. Now, what's the reason why you're seeing a volume control thing over here? Do that again, Jim. Because we're just speeding up the electrons very lightly. We really turn it up. You can push quite a bit of current through there with that, and then we can turn it down almost to nothing. That's good. This design of tube here is look at that. That's still it's still glowing, which is probably just a little bit. No, not warm. Okay, yeah. Okay. This particular effect really led a lot of tube builders and experimenters to move on to even finer levels of putting different types of fluorescent materials inside of these tubes. We'll have the lights, please. Are we at the? No, it should be. Yeah, we should. The next tube that we're going to show you, I think, is without a doubt the finest piece that I have ever seen, and I've seen a few. Finest piece of tube, discharge tube. It is a piece of workmanship that actually probably put that on the big coil and turn it down. It might be the best thing. We're looking at the beginning here. I'll show this tube while Jim hooks this up. Inside of this tube here, there is a butterfly constructed out of some metal, and there are, when you see it, you'll understand. Let me just go around with this a bit here. Thank you, Bill. Just to show you what it is. It's just a bunch of rocks in the bottom of it. Let me just do this a little bit better here. Yes, they had done experiments to see that they would work. I don't know exactly what they are, but it's just basically some fluorescent rocks, and you see there's powder on the walls of the tube, and on the top there are just two electrodes, and it doesn't matter, they're both aimed at the center, so when you change the polarity of the tube, it merely moves the cathode beam, the beam of electrons, over to the other side, but they still wind up striking the rocks anyway, and there isn't a big problem with that. This is just a very, very common and basic tube for this. However, oh good, we have a good stand, I don't need to hold that. This next tube is truly, well, I think that my words are only going to detract from it. Let's put the bricks to it, as they say. And Lights out, please. Watch closely. Reverse the polarity. Yeah. Maybe if you want to stand up in the front rows, don't come up too close, but just, we don't want to turn that way down. To turn it way, way, way down. Look at that. Now cut it. Cut it off. Look at the time it takes for it to relax. I give it a little jolt, you can see. But notice the various colors in the wings. There's red, green, orange, yellow, Kelly green. The eyes, the red eyes in that thing is really, Jim, you've just got to see this. Yes, we do have documentation. I just don't happen to have it right on the tip of my tongue to tell you all of the phosphorescent materials that were used to do this. And on the base of this glass, you can also see that there is a shadow of the butterfly cast on the base of the tube. Germany. This is a German. Is this Otto Pressler? Or Rudolf Pressler, rather? Yeah, it might be a Rudolf Pressler, if you want to know the company that was really famous. Don't run that too long. Let that relax now. And it'll take it a while for that thing. Is it warm? Yeah, we want to be careful of that. Turn it toward the camera. About 1890. Okay. Run it low. Okay, camera ready? Go ahead, see what you can do. Yeah, it's there you go. Yeah, you can see it. But you can see there you can see the effect. Look at the eyes. The eyes, even the proboscis or the antennae are also done. You can see them sitting up and twirling around the top. It is exceptional. You know, an exceptional tube. I imagine a little bit. You know, I mean, what can I say? It's. No, I don't think so, but have you ever spent any time in Victorian England and looking at, you know, I mean, well, I mean, I think it's part and parcel with a devotion to quality and to show the mysteries and wonders of nature by virtue of doing something as ornate and as devoted as possible to, you know, make it to support that kind of thing. Well, I imagine that was probably possible. Well, in 1890, you know, there was there was people using a fair amount of electricity by that time. But you're right in the sense that nobody really was using a lot of electricity. This definitely was something. I think the point you're making, which is good, is that this is definitely something you could take into your house, and with a battery and an induction coil, you could really have a look at some of the mysteries and wonders of nature, and really get, you know, and see something really. I mean, nature's really performing for you here. Well. Yeah, I suppose you could look at that, but I think you could. Yeah, I mean, I don't think that. Yeah, you do it. Well, there's some of us here that have been doing this for, I don't know, 30 years, 40 years, some amount of years, and I don't know. I've got some problems, but I don't. None of them related to that, you know. What's that? No, but you know, I certainly have a family, and I was well into these things, X-rays and stuff, 30 years ago. I mean, I don't want to sort of, you know, let's find some. Can't find wood anymore. No, I mean, what can you do? According to the, I don't know, you know.